All right, here we go. This is our starter problem for the day, and this is just an order of operations type problem, which you have to remember, you have to do parentheses first, but there is no parentheses in this problem. And then you'd look for any exponents, but I don't see any exponents in this problem. So I move to multiplication and division, and yes, there is some multiplication here between the 7 and 4. 7 groups of 4, 7 times 4 would be 28. Now the problem would read 3 plus 28, which when we add, we would get 3 plus 8 is 11, but carry the 1 makes that 31. And that would be simplifying the original problem. What we want to point out here is that a lot of students, they're likely to do, if they're not used to this, okay, so you may need some more practice. You may have made the same mistake. If you got 40, you may have done 3 plus 7 first, but that is out of order. And so to maintain order here, we have to do the multiplication first, and then we can do the addition. Okay, here's our objectives for 2.1. I can factor in and prime factor values. There we go. I can find the greatest common factor between values. I have to put that in. I can find. And then I can find the lowest common multiple of values as well. We'll go over each of these, and then hopefully you'll be able to do them by the time we finish. So this is a slide we've seen already where we're looking at something like 9 times 8 is 72. 9 and 8 are called factors, and when you multiply them, you get a product. What we're going to be looking at today is essentially we're looking at the product and then breaking it back up into factors. And this kind of goes back to things that we've learned already, such as sometimes math is what you want it to be, right? So, for example, sometimes it's easier to see 72 as 9 times 8. Some students may even say that it would be 6 times 12. Or I think it'd be 3 times 24. Could be wrong there, but something like that. You can break 72 up into as many ways as you'd like. Even like 1 times 72 would work. This one's just showing 9 times 8. Again, it's what do you need? Like, why are you doing this? Why would you want to break this up? Well, we'll get into that in today's lesson. So part of that is memorizing your first 12 multiples, because if you can, then you can find, for example, 72 right here, which would have been 8 times 9. And 9 times 8, that's, well, I guess there's, like 72 right there, right? You could have done as 12 times 6. But if you have this table memorized, you can kind of go backwards as well, right? So this is a multiplication table, meaning you'd be originally looking at 6 times 12 to get 72. But now we're going to start at 72 and say break it up into 6 and 12. So if you have this memorized, it's a little bit easier to break those up, but we can use division to do it as well. So division, remember, you have a dividend, and then you divide that by a divisor in order to get your quotient. We're used to this symbol for division, but it's possible you may see it in some kind of fraction form, which I believe you will in this module. So again, this is a slide we've seen already. How many times will the divisor fit into the dividend? That's what a division problem is really asking. And then we already know if it doesn't fit in evenly, then you get some kind of remainder. We're not really worried about remainders so much anymore, but again, we may see that a little bit, I believe, in Module 4, but in Unit 2 here, in Module 2, we're looking at fractions, and then the process to simplify them requires us to take a value, divide it, in order to figure out some of the factors that may be involved with what would be the product. So again, this is just a slide. We've seen this already. We've seen the symbol already. You may see division as a fraction. Sometimes it's just a slash. And you could still call this a fraction, by the way. But in addition to that, we've seen this long division. So yes, it's possible to take multiplication like this and simply change it into a division problem, such as 3 times 4 equals 12. Yeah, we've seen this already. You can break this back up into 12 divided by 4 is 3, or even 12 divided by 3 is 4. Now again, once we start looking at real fractions, we're going to have to say, well, why would we want to do this? And again, you can just break it up into factors, which may help us to get there. But the truth is, if you can understand, you just divide this value by 4, and maybe another value is divisible by 4, you can do it simultaneously or kind of both at the same time. Now, that doesn't have to make a ton of sense. Really, what we're going to be doing is looking at a value and see if it can be divided by specific values. Okay, and this is why it's important to remember your multiplication table, because even like the objective says, we're going to be looking at multiples of values as well. So divisibility means that we have a value and it can be divided by maybe a value or more values, okay? And we're looking specifically at natural numbers. We're not worried about decimals or fractions or even negatives right now. We're just looking at natural numbers. In fact, notice it's natural. It's not even whole numbers. We do not want to be dividing by 0 at this time. So ignore 0, ignore any negatives, decimals, and fractions. We just want to know if a number is divisible specifically or can be divided by specific values. So based on what we know then, we should be able to answer this question. Given that 7 times 6 equals 42, check all the statements below that are true. So now before we do this, okay, there's some vocabulary down here. In this problem, we see that 7 times 6, 7 and 6 are both what we call factors. And then 42 would be the product of those two factors. Now, if we change this into a division problem, which we can, you would take the product, which is 42, and then you can divide it by either one of the factors, such as, let's take it the 7 first, and then it would equal the other factor. So that's why, like we saw in the, I think it was 2 slides ago, you see 2 division facts that go along with the multiplication fact. Okay, so let's interpret this. We got factors and then we have a product, but then it's showing 42 because it's the product in its related fact family division problem. The product becomes a dividend, okay, and then the factors are either the divisor or the quotient. Divisor, quotient. So, since it's dividing 42 by 7, and 42 can be divided by 6 in order to get these quotients, then we know that 42 is divisible by 7 or 6. So now that hopefully we understand that right there, we can go through each of these statements. So first off, 42 is a factor of 6. No, 6 is showing as a factor of 42. So no, this one is false. I'm just going to cross it out. Again, I'm not saying it's true, just crossing it out so we know it's not true. Okay, well, is 42 a factor of 7? No, 7 is a factor of 42. So again, it's just kind of reversed. If we were to change those, it would be a true statement. But the way it is written there, it is false. Well, up here, it's saying 6 is a factor of 42. Yeah, 6 is one of the factors of the product 42. So this one is true. I'll put a check mark in there. Now it's saying 7 is a factor of 42. Again, 7 is showing as a factor right there. So I'll put a check there because that is true. Now we see here 42 can be divided by 7 to get another natural number. So 7 is divisible by 42. No, it would be 42 is dividing or is divisible by 7. So between these two statements, this is the true one. 7 is not actually divisible by 42. It would have to show 7 divided by 42 in the fact family in order for this to be a true statement. But it is not. Now it says 42 is divisible by 6, which again, that would read as 42 divided by 6, which is one of the statements in our fact family. So again, we can say that is a true statement. So 6 is divisible by 42 down here? No, that's false, because it would not show 6 divided by 42. Okay, and again, if you switch those, it would be true. All right, so this one, we're going to do the same thing. Here we have 27 divided by 3 equals 9. Now, as a division problem, the dividend just stays a dividend, meaning it's at 27. It would still be division, but what we're going to do is we're going to switch the quotient and the divisor. So that would be then 27 divided by 9 equals 3, which is also true. Then we can also change this into its multiplication fact in this fact family, which is where we take either one of the quotient or the divisor, which would be 3 and 9. We write this as a multiplication problem, and then it equals the product, and the product is the same as the dividend, which is, in this case, 27. So again, at least for the multiplication problem, we have our factors, and then 27 is the product. So that also means that 3 and 9 are factors of 27. So let's go through each of the statements. I'll start in the top left and go down. 9 is a factor of 27. Yeah, that's what this is showing right here. 9 is a factor of the product 27. So right now that is true. 27 is divisible by 9. This would be the same as showing 27 divided by 9, which, yeah, we can see that one right here, so it checks off. Next, it says 9 is divisible by 27. That would show 9 divided by 27 like this, which is false. So this one we're just going to cross out. 3 is a factor of 27. Again, that is shown in the multiplication problem right there, so we check that one off too. 27 is divisible by 3. If we would write that as an expression, it would be 27 divided by 3, which was the original statement they gave us up here. So yes, it is divisible by 3, which would be 9. Now, 27 is a factor in both of these next two statements. No, 27 is never a factor. It is a product, though. So this is where our vocabulary becomes very important in these types of problems. And then again, 3 is divisible by 27, which as a statement would read 3 divided by 27 like this. But again, we don't see any of these statements in the fact family show 3 divided by 27. So this one is false, and we have the 4 statements which are true. So this brings us into divisibility rules. And I'm going to start with 2 and 5. I'm going to come back to 3, but let's do 2 and 5 first. So a number, any number, doesn't matter how big it is, so it can go into the thousands, it can go into the millions and billions and trillions. It doesn't matter how big or small it is. You could have a number that's just in the ones. Maybe it's a tens and ones or hundreds, tens and ones. It doesn't matter how big or small the number is. If it is divisible, or if it can be divided by 2, then in the ones place value, which is just the number furthest to the right for us, we're not looking at any decimals, number furthest to the right will either be a 0, 2, 4, 6, or 8. Meaning if it's even there, then we know it is divisible by 2. Now again, I'm going to come back to 3, but if it's divisible by 5, again, the reason why I'm doing this one is because you're just looking at the ones place value. Seeing if a value is divisible by 2 and 5 is just a matter of looking. Can you see specifically in the ones place value, and for divisibility by 5, it has to be a 0 or 5, okay? If I look in the ones place value, let's say that I saw a 7. Okay, if I see a 7 there, it is not divisible by 2 or 5. Okay, so if it's divisible by 5, I have to see either 0 or 5. If it's divisible by 2, it has to see a 0, 2, 4, 6, or 8 in the ones place value. Again, that means I don't care what is in the tens, hundreds, thousands, 10,000s, or 100,000. I don't care about any of that stuff. All I care about is looking and seeing what is in the ones place value. Okay, now 3, this takes a little bit of work, but what you're going to do is it's the sum, which means you're looking at an addition problem of all the digits, and then you see if that number can be divided by 3, okay? Well, how do we know if it's divisible by 3? So in our multiplication tables, we're looking for something that is also something multiplied by 3, like 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and so forth, okay? Really, we shouldn't get up necessarily that high. But the truth is, if you can narrow that down, then you can take that number and see if you can add those numbers and see if it's divisible by 3. It still works. So divisibility by 3 takes a little bit more work, but divisibility by 2 and 5 is just a visual check. You're just looking at the ones place value specifically. Now divisibility by 3 I think it's going to be better if we see an example of that. Now, a quick note on divisibility rules. If a number is divisible by another number, it means that you have nothing remaining. So if you do the long division, you would have no remainder left at all. And we'll have to keep that in mind because, for example, if I add the sum of the digits together and it's not divisible by 3, you could still divide by 3, but then you'd have a remainder. Same with 5. Let's say you're looking at 5, maybe a number is divisible by 5, but you don't see in the ones place value 0 or 5, then you can still divide by 5, but you have a remainder. Therefore, that number is not divisible by 5. But first, there are some other side divisibility rules. I wouldn't necessarily say you have to memorize these because really we're just looking to see if we can divide by 2, 5, or 3. Which these ones all fall under anyways. So 4, for example, it's divisible by 2, but then it can be divided by 2 again. So another way to do it is you look at the last 2 digits and see if they are divisible by 4, meaning that if it needs to be a multiple of 4, meaning 4, 8, 12, 16, 20, 24, 28, 32, 36, something like that. It needs to be any of those numbers, okay? If a number is divisible by 6, it has to be divisible by 2. Again, that's just looking at the ones place value and 3. So again, you would still look at the ones place value, but then to see if it's divisible by 3, you actually have to add all of the digits together to see if it's divisible by 3. Now again, if we do these separately, like we were looking at the last slide, then we would see it's divisible by 2 and then divisible by 3, and then we would just know it's divisible. That whatever the number is, it would be divisible by 6 as well. So a number will be divisible by 10, and this kind of falls under the divisibility by 5, but also 2 rules. Then you're looking at the ones place value. You have to see a 0 in the ones place value. Again, we don't care what else is there on the number. In the ones place value, we'll see a 0. So if a number is divisible by 9, it's divisible by 3 2 times in a row. Okay, so you can divide the number by 3, see what that is, and then you can divide that number also. It would be then divisible by 3, that second number. These ones I don't necessarily think it's so important to memorize because, again, 9, you're just dividing the number by 3 and seeing if that number is divisible by 3. 10 is just kind of visual check for 0, but you're already checking for 0 for both 2 and 5. And then 4, again, it's like divisible by 2 twice. And then 6, you're, again, 2 and 3. So we see 2, 3, and 5 are kind of the basis for these rules of divisibility. Why is there not a divisibility rule by 7? Well, 7, we're just pretty much saying you're probably going to have to use long division to see if a number is divisible by 7. The same would be true for numbers like 13, okay? So which of the following is 2,646 divisible by? So we're going to start with 2, and we know 2, a number is divisible by 2 if in the ones place value there has to be a 0, 2, 4, 6, or 8. Okay, well, do I see in the ones place value, which we will identify here, there's the 6. Yep, a 6 is there, so yes. Which of the following is 2,646 divisible by? I would say 2. Okay, so there's that one. 3, we got to take the sum of the values, okay? So sum of the, well, I'll say digits, which is 2 plus 6 plus 4 plus 6. Now, when you do that math, you're going to end up with 18. Okay, and 18 is a multiple of 3, but let's say we didn't know that. Okay, then I would do 1 plus 8, which is 9, and I know 9 is a multiple of 3. So you can't just do it that way, and then you can say, well, yes, I added these numbers together, got 18. Some of you know 18 is a multiple of 3. That'd be 3 times 6, but if you didn't, you can just add those numbers together to get 9. And you'd have to have, if you're going to do it like that, you have to have at least the multiples of, first 3 multiples of 3, 3, 6, and 9. So yes, 2,646, if you divided it by 3, you would have nothing remaining. Okay, so 5, again, like we know already, hopefully, if a number is divisible by 5, then in the ones place value, you have to have a 0 or 5. And, well, up here at the top, we've already pointed out the ones place value is a 6. So is it divisible by 5? I'll put a slash through it to represent that it is not divisible by 5. Okay, let's go to 4 then. In fact, let's look at all 3 of these, okay, because we have these 3 basic ones down, all right? So if a number is not divisible by 5, then automatically it cannot be divisible by 10. Now, tens doesn't necessarily have to be divisible by 5, or it has to be divisible by 5, but under the condition that the ones place value is a 0. Okay, so if the ones place value equals a 0, then it is divisible by 10. But again, it's just a visual check. I see a 6, so it can't be divisible by 10. Now again, before we get into 4 and 9, I would go to 6, and I see up here that we've already written down that 2,646, the number, the value, is divisible by 2, and it has to be and 3. So yes, this one, 2,646, is divisible by 6 because it checks off the 2 and the 3 above. Okay, well, is it divisible by 4? So on the last slide, we said that the last 2 digits, which is the tens and ones place value together, need to be divisible by 4. So in other words, it needs to be a multiple of 4. Well, the last 2 digits there are 4 and 6. That would be 46. And 46 is not a multiple of 4. We know 4 times 10 would be 40. 4 times 11 is 44. 4 times 12 is 48. So it is not divisible by 4. Now this also means, let's say you were to divide this by 2. That means that if you were to find that quotient, that new number, which appears to be 1,323, would not be divisible by 2. Okay, so you can divide this number by 2 once, but not twice. Is the number divisible by 9? Well, if it is, then I should be able to take 2,646 and divide it by 3 twice. Another way that they'll say that is that what you'll do is you'll take the sum of the digits, and then when you add them together, that number has to be divisible by 9, which it is. We know that because by adding those 2 numbers, we got a 9 as well. So we will say that this number is also divisible by 9. Now you could check. You're not supposed to be using calculators yet, but you could check. You could just take this number, divide it by 2, see if you get a whole value or a decimal value or a fraction. We should not see any fractions or decimals if it is divisible. So yeah, if you were to put this divide by 2, 3, 6, or 9, you would get whole values. And so this works for these 4 numbers, but not 5, 4, and 10. So which of the following is 385,875 divisible by? Well, first off, if it's divisible by 2, then the ones place value needs to be either 0, 2, 4, 6, or 8. And right here in my ones place value, I see a 5. So since it's a 5, not a 0, 2, 4, or 6, in other words, it's not even, this number is not divisible by 2. Now again, I'm going to jump to 5 because 2 and 5 are just visual checks. So if it's divisible by 5, the ones place value will be a 5 or a 0. Well, I do have a 5 there in my ones place value. So again, on this one, we do see that this number is divisible by 5. Okay, is it divisible by 3? So again, the sum of the numbers. So we're going to take the sum of the digits, rather. So 3 plus 8 plus 5 plus 8 plus 7 plus 5 equals, let's see what that is. So 3 plus 8 is 11, plus 5 is 16, Plus 8 would be 24. Plus 7 would be 31. Plus 5 would be 36 there. Now, let's say that you didn't know that 36 was divisible by 3. Okay, we'll just add these two numbers together. And then you see that you get 9 out of that. And 9 is divisible by 3. So we would say here that the number is divisible by 3. Okay, so let's go down here to these other ones. Again, I would probably start with 10. Since we do not see a 0 in the ones place value, it's not divisible by 10. Okay, also, it wasn't divisible by 2, so it cannot be divisible by 4 either. And since it was not divisible by 2, it is not divisible by 6. Now be careful, because some students say, well, it's divisible by 3, so it's divisible by 6. No, it has to be 2 and 3, not just one of them. So is it divisible by 9? Yes, it is, because 36 is a multiple of 9, but again, we added the 3 and 6 to get the 9, which means it is also divisible by 9. Okay, so we've seen this already. What is a factor? A factor is a number that's being multiplied by another value. Okay, so right here we're only showing 2 factors. It's possible you could show 3 factors in some numbers, but this one would just be 5 times 2 is 10, and that's all right. 5 and 2 are factors. And then 10 is a product. Okay, so we're going to need this. This is our fractions unit, and so we're expecting to use some of this factoring. Again, but to go back, what they're going to do is they're going to give us the 10. What we have to do is split it up between 5 and 2. That's going to help a ton when we get into simplifying fractions, which is why we were just looking at, okay, well, what can you divide 10 by? You can divide it by 10, 5, or 2. Okay, and that's going to help us to figure out how to simplify fractions in the future. So understand that's coming, but we have to be able to know if a number is, if it can be divided by other whole numbers, okay? So again, this would be 5 and 2. Now, on the assignment, they're going to say, all right, just determine if a number is prime or composite. So if a number is prime, its only factors, meaning the only way you can obtain that number through multiplication is by multiplying 1 and itself together. Okay, a number like that would be like, let's say number 5. Okay, 2 is prime, 3 is prime, but 5. Let's look at 5. So 5, what can I divide 5 by? Well, I could divide it by 5, but what would I multiply 5 to get 5? It's 1. And that's all I can multiply it by. As long as we're just looking at whole numbers, and that's all we are looking at. So 2, 3, and 5 are kind of our basic prime numbers. 7 is prime, 11 is prime, and 13 is prime. That's about as high as we need to go. Of course, there's more, but that's as many as we need. If a number can be divided by something, meaning it has some kind of divisibility rule applied to it, then it is called composite. So for the 2 selections that you have on the assignment, you have either prime or composite. Again, if you know that it's divisible by some value other than 1, then it's composite. Now, 1 is not prime or composite. We're not worried about number 1. I just call it the identity property, but it's classified in several different ways. For example, that it's odd. Not that we need to worry about 1, okay? So factors, prime would indicate that you don't really have any other factors other than 1 in itself, but composite means that you can divide it by something else. So let's go back to that number 10, right? Now you could say, well, can't you express 10 as 1 times itself? You can, but that's not the only pair that I can use as factors. I could also take 2 and multiply it by 5, and that's what makes it a composite. Now, there could be more for some numbers. 10 just has these 2 pairs. Factor pairs is what I'm going to call them. But we don't need to see any more than just anything else than 1 in itself in order for it to be composite, okay? So once you see that it's something else, even though there could be more for some of the numbers, don't worry about those in order to know it's composite. So if it's composite, just check your divisibility rules. Start dividing the number by 2, 3, 4, 5, 6. Really just, again, I would say 2, 3, 5, and 10. Because if they are, then it's automatically composite. So we're looking for only the factors which have a remainder of 0. That's true. That's what makes it divisible. Again, we don't need any repetitions or many different sets or pairs. We just need to see one other pair in order for this to work. So we're going to focus, though, on just really just 2 and 3 and 5, okay? But the nice thing about 2, 5, and 10 is that they are just visual checks. Just look at the number and see in the ones place value what that number is. And if it's 0, 2, 4, 5, 6, 8, then we know that the number is divisible by either 2, 5, or 10. Okay? So let's take a look at some examples. So identify the following as prime or composite. So again, my main divisibility rules are based off of 2. Okay, so 2, we're looking for in the ones place value. We should have 0, 2, 4, 6, or 8. Then we'll look at 5, which in the ones place value should be a 0 or 5. Okay, now again, I'm going to skip 10 just for the sake of space. 3, then again, it's a little bit more work to check 3, but you just add the digits and see if the sum is divisible by 3. That's it. So again, I don't need to check 9. I don't need to check 4. I don't need to check 6. I don't need to check any of them, but these 3 really. All right? And that's why we went over those first. Let's start with 73. So 73 in my ones place value here means that it's not divisible by 2 or 5. Okay, so we're going to take those numbers, we're going to add them together. That would be 7 plus 3, which is 10. Now, if you didn't know, 10 is not divisible by 3, but you could have added those numbers together to get 1. Again, 1 is not one of the first 3 multiples of 3. So in addition to this not being divisible by 2 or 5, it is also not divisible by 3. And that's pretty much all we got to check for this assignment in order to know that this specific number here, 73, is prime. So that means you could split it up into factors, but that factor pair would just be 1 times 73. All right, now let's go to 97. So 97, again, in my ones place value is a 7. So right off the bat there, I know that 97, not divisible by 2 or 5. Okay, but is it divisible by 3? Well, if it is, then I should be able to take those two numbers, 9 and 7, and if I add them together, it should be a number that is divisible by 3. Now, if you didn't know 16 is not a multiple of 3, add those together, you get 7. Well, 7 is not divisible by 3 either, which means that not only is it not divisible by 2 or 5, but it's also not divisible by 3 either. Okay? So this one, 97, we also say it is prime. Okay, well, how about 93? Well, we got the 3 in the ones place value. Again, that's just a quick visual check. So this one here is not. It's not divisible by 2 or 5. But let's go ahead and check to see if it's divisible by 3. Well, if it is, we'd take 9 in the tens place value, 3 in the ones place value, and add them together to get 12. Again, you can just add those numbers together to get 3. So I see that 93 must be divisible by 3, which makes 93 composite. All right, there's that. Next, let's check 59 there. So 59 in the ones place value is a 9. So I know right off the bat it is not divisible by 2 or 5. Okay, so let's go and check 3. So I'm going to go in here. I take my 5 and my 9 in the place values, I add those two numbers together to give 14. Again, if you don't know that 14 is not a multiple of 3, you can add those together to give 5. Now, 5 itself, again, is not a multiple of 3. So this number, not only is it not divisible by 2 or 5, but it's also not divisible by 3 either. Okay? So since it's not qualifying under those three, 59 must be prime. The last one we'll check is 48 there. So 48, well, right off the bat here, I see an 8 in my ones place value. That shows me that it is divisible. So it is divisible by 2. So that automatically also makes 48 composite. All right, let's go and list the factors of 29. So we're just looking for anything that we can divide it by, right? So 29 in my ones place value is a 9. So right off the bat there, I know it's not divisible by 2, 5, and I'll just throw in 10 there. Because again, it's just a visual check with 2, 5, and 10. If it was divisible by 2, it'd have to be a 2, 4, 6, 8, or 0. If it was 5 or 10, 5 would have to be 0 or 5. 10 would have to just be 0, but it's none of those. It's a 9. So now I will check to see if it's divisible by 3. So I'm going to take the 2 and the 9 as separate digits and add them together. 2 plus 9 would be 11. 11 is not a multiple of 3, so it's not divisible by 3 either. Okay, so it's not divisible by 2, 5, 10, or 3. It's not a multiple of 7, just kind of checking offhand, and same with 13, which is kind of the unusual ones. So this one means that 29, in fact, is prime. Now you could check more values if you'd like, but the more you check, the more you realize that the only way you can list the factors of 29, which we still want, it would be to take 1 and 29, and those would be the factors of 29. Because it's prime, you can only multiply it by 1 in itself in order to obtain that as a product. Okay, so let's look at the factors of 96 there. 96, pretty good number. First up, I can see that 96 has a 6 in the ones place value. So it is divisible by 2. It is not divisible by 5. And again, I'm just going to throw this one in there because it's a quick visual check, not 5 or 10. Okay, so if it's divisible by 2, we can find the other factor that goes with the 2. But before we do, let's see if it's divisible by 3. So I'm going to take the 9 and the 6 and add those together, and when I do, I get 15. 15 is divisible by 3, but again, just in case you didn't know, you could add those together, 1 plus 5 to get 6, which means it's also divisible by 3. Okay, so it is divisible by 3. Now, since it's divisible, since it's divisible by 2 and 3, it is also divisible by 6. Okay, so that was nice. What I notice here also is that it is not divisible by 9, though. 9 plus 6 is 15, which is not a multiple of 9. And even adding those together, we didn't get a 9. So it is not divisible by 9, and that's okay. But it's at least divisible by 6. Let's see, 2, 3, and 6 is all we got right here. Let's go with that. Let's see what happens when we do that. Okay, so what are the other factors? So list the factors of 96. All right, fair enough. We have 2, 3, and 6 so far. We can list these in pairs, though. So what I'm saying is let's take the 96 and divide it. Let's divide it by 2 first and see what its other pair is. Now, I'm going to do this fairly quick, so you may have to slow down the video or pause it to keep up. But 2 goes into 9 4 times. 4 times 2 is 8, so we used up 8 of those 9, and we're left with 1. We'll drop the 6. 2 goes into 16 8 times. Okay, so the 2, this means that 96 is the same as 2 times 48, which would be 96. And you can check that multiplication if you'd like. But this means that I also can include 48. So I guess I'm gonna give myself some space there to list them in between. Oh, you know what? I forgot one. I forgot 1. 1 and 96 itself. Those would be factors as well. Okay, but we also said that 96, we know, is divisible by 3. So let's go and divide it by 3 and see what else we get. 3 goes into 9 3 times. 3 times 3 is 9. We used up all 9, so we'll drop the 6. 3 goes into 6 twice. So again, this means that 96 could also be shown as 3 times 32 to get 96. So again, let's put the 32 out here. Okay, let's go ahead and take 96 again and divide it by 6, then, because it should be divisible by 6. 6 goes into 9 once. 1 times 6 is 6. When I subtract, I get 3 left over. I drop the 6. 6 goes into 36 6 times. So the 6 would be paired with a 16. Now, as it turns out, there's more as well. But this one just, it kind of happens offhand. So again, this is where you may have to do some guess and test. But 96, again, this really just goes back to our multiplication tables, our multiplication table. But 96 is a multiple of 12. Okay, or, and I'm kind of giving away the answer here, but it's a multiple of 8, meaning 8 goes into 9 once. 1 times 8 is 8. When I subtract 9 minus 8 is 1. I drop the 6. 8 goes into 16 2 times. So 96 could also be shown as the factors 8 times 12 is 96, which gives us a new factor pair, 8 and 12. Now, we already know it's not divisible by 9. It's not divisible by 10 or 11. So this actually is all of our factors of 96. So how do we know it was divisible by 8? Well, what you could have done is when you divided it by 2, you had 48, which means, oh, I'm probably missing a factor, aren't I? It means that since our, when I divided by 2, I got 48, which is still divisible by 2. It means that we could have taken 96 and divided it by 4 as well. So I missed one, didn't I? 4 goes into 9 2 times. 2 times 4 is 8. When I subtract, get 1 left over, drop the 6. 4 goes into 16 4 times. So in other words, in between there, I also need to include 4. And back here, we'll put in 24. Okay, so the orange numbers, I'm just trying to fit them in from order from least to greatest. I don't know why I'm doing it, I'm just doing it. So once I divided by 4, though, it was still divisible by 2. So I'd say 4 times 2 is 8. Now I know 96 would be divisible by 8 as well, which we already have. But I have that included now. I almost missed it, right? So you got to be careful on these. 96, it's divisible by many numbers. 1, 2, 3, 4, 6, 8, 12, 16, 24, 32, 48, and then itself, of course. So we're seeing a quick review on just some of the vocabulary with exponents. What we remember here is 5 is called the base here, and then 4 is the exponent. But this reads, if you just saw this math symbols here, it's like math hieroglyphs, this would read 5 to the power of 4, meaning 5 would end up being multiplied by itself 4 times. So to expand this into its repeated multiplication, you'd have 1, 2, 3, 4 5s, but all of them would have to be multiplied together. Okay, and that's what an exponent tells us, is how many times the base is being multiplied by itself. Now, the reason why we're going to do this, or why we're seeing this again, is because when we start using prime factorization for whatever values they give us, we are going to need to use exponents if we see any repeated multiplication. So you have to keep that in mind, but it goes with the definition of what exponents are. So prime factorization. Okay, so we already saw kind of our first few basic prime numbers, which would be numbers such as 2, 3, 5, 7, 11, and 13. I really hope we don't see any prime factors beyond this, but I can't guarantee that we won't. Others would include 17 and 19, for example. But factoring is where we take a number and we break it up into its factors. Remember, those are the multiplied values. So one of the examples we saw already is now we're saying you're going to start with 10, but you're now going to change it into 2 times 5. So again, it helps to know divisibility rules, because if you didn't know that you could divide 10 by either 2 or 5, then it would be fairly difficult to figure out what the factors are, which is another reason why we're encouraging you guys as soon as possible to memorize that multiplication table. Now, 2 and 5 are prime factors, but we saw in the last example, you could have taken 96, for example, here, and you could have said, you know what, it's 8 times 12, neither of which are prime. Okay, so you can factor out a value without prime factorization, but prime factorization is really what we're looking for. Now again, all of this is in an effort to help us with fractions later on. So we have to have these skills down before we get into the real fractions, which we will, just not yet. Prime factoring again is just breaking it up into its prime factors, such as 2 and 5. You never include 1 in your prime factorization because 1 is not prime. So yeah, again, here's another example. 25 as prime factors would be 5 and 5. Actually, there's no other factors you could use, I guess, other than 1 and 25, but that doesn't really help. 5 is prime, so 5 times 5. Now, 20 could be shown as 4 times 5. 5 is prime, 4 is not. It's factored, but we can take the 4 and split it up. So I'll kind of show that there. The 4 has been split up into those two 2's, and now its prime factorization is 2 times 5. If you plug that into a calculator, you'd get 20, or just do the multiplication. But here's what we want. This is where the exponent stuff comes in. There's repeated multiplication with the 2's. So we write it as 2 to the power of 2, and then times the base prime factor of 5. And then it would be considered prime factor. So if you try to put something like this into the assignment, it will not accept it for full credit. You need it as an exponent like this one, if it can be. So again, essentially, we're just dividing like 25. You say, well, I divide it by 5. 25 divided by 5 gives me the other factor of 5. Or 20 divided by 4 would be this 5. 20 divided by 5 would be 4. Either way you want to look at it. We're looking at what we can divide these numbers by, which, again, is why the divisibility rules are so important. So 52, for example, we know we want to find its prime factors. Now, what I'm going to do is I'm going to use something we call a factor tree. Okay? Meaning I'm going to take my 52 and I'm going to just branch values off of it. Okay? Now, as I branch them off, I'm really looking for, right now, I want 2 numbers that I can multiply together to get 52. So this is where the divisibility rules come into play. I got 52. Is there a number I can divide it by that won't have any remainder? Well, right off the bat, I see the 1's place value is a 2. So I'm just going to start there. It could be divisible by 3 or some other value, but I just don't care about that. I know it's divisible by 2, which is going to should make the division fairly easy. 2 goes into 5 2 times. 2 times 2 is 4. So we used up 4 of the 5. We have 1 left over. Drop the 2 in the 1's place value. 2 goes into 12 6 times. 6 times 2 is 12. So yeah, we get a remainder of 0, just as planned, which means that 2 times the 26, if you were to multiply these two, you would get 52. Now, the way factor trees work is usually once you see a prime factor, you circle that number so that you know no other branches should proceed from that prime factor. But 26, I know I can factor this one out as well, because 26 is divisible by 2. How do I know it's divisible by 2? Because of the 6 in the 1's place value is even, so I know it is divisible by 2. So 2 will be this factor here, but what would be the other one? Well, 2 goes into 2 once. 1 times 2 is 2. When I subtract, I got nothing remaining there, so I'll drop the 6. 2 goes into 6 3 times. And yeah, 13 we've already shown is a prime factor itself. Again, you could try to divide if you'd like, but it's not divisible by anything other than 1 in itself. So that is its prime factor. Now, well, I'm going to show this a little different, but 52, instead of showing it as 52, we are now showing it as 2 times 2 times 13. But as good as that is and as much work as we've done, I have a base 2 right there, and I see it 1, 2 times, so it's really 2 to the power of 2 times the 13. And that's how we're going to show our 52 in order to get full credit on the assignment. Now, I'm okay with this one. I'm also okay with this one unless we've been directed otherwise, which we'll have to find out when the next test comes out. But for now, if you can get to this point, it shouldn't be a long bridge to cross to get to this point right here, right? As long as we have our exponent stuff down. So this is the one where you're going to want on the assignment. We'll have to check on this one if it's good for tests. So let's list the prime factors of 65. So again, I'm going to use a factor tree. Now again, you do not have to show it like this. A factor tree is really just a nice way to organize the work. Okay, so I'm going to take 65. Okay, is there some number I can divide by 65? I apologize, that I can divide 65 by. Yeah, in the ones place value I have a 5, which is prime. So I know I can divide 65 by 5. 5 goes into 6 once. 1 times 5 is 5. So we got a remainder of 1. Drop the 5 to make it 15. 5 goes into 15 3 times. 3 times 5 is 15. Nothing remaining. So that would be 13, which also is prime. As it turns out, the only two prime factors of 65 are 5 and 13. Now, you want to be careful. It's possible, and I don't know that this is going to happen, but it's possible they may give you a prime number to start with. So if they say, list the prime factors of some number, like 17, for example, you just say, well, it's prime. So it doesn't have any prime factors. Of course, you have 1 in itself, which just is its own prime factor. This one, though, 65, there was no need for any exponents. So that's just it, 5 times 13. And if you list it as 13 times 5, or 13 and then 5, it doesn't matter. You're going to get the same answer. So that would be okay. Okay, common factors. So matching or common factors of 2 or more numbers. 1 could be included, okay, but we just don't usually focus on 1 as a common factor because 1 is actually a common factor for any number. What we're looking for is seeing if we can look at 2 numbers and determine if they can be divided by the same value. Prime factorization may help here, but really we don't need prime values in order to make this happen. All right, for this problem, we want all the common factors of 16 and 18, meaning we want to list all the factors of these values and then see which ones are in common. Okay, so I'm going to look at 16, and I'm looking for factor pairs, meaning 2 numbers that multiply together to get 16. Well, I know I can multiply 1 and 16 together, and that's good. I know 16 is divisible by 2. That would be 2 times 8. And I'm not doing the long division there because that fits into our multiplication table. It's not divisible by 3, but I can divide it by 4. That would be 4 times 4. So the factors of 16, I'll go and list them over here. Factors of 16 would be 1, 2, 4. I'm not listing 2 4s because I don't really need them. And then 16. Okay, 4 is its own factor. We don't need to list it twice. It's just a factor. That's all we need. Next up, we'll look at 18. Okay, so 18, of course, 1 times 18 would be 18. 18 is divisible by 2. That'd be 2 times 9. Again, this just goes back to our multiplication tables. 18 is also 3 times 6. And that's as far as we can go there. So my factors of 18 are 1, 2, 3, 6, 9, and then 18, of course. So what we need now is to find the common factors, which I'm just looking for matches. So I got the 1s. So let's put that in there. 1 is a common factor. 2s are common. 2. 3s are not common. 4, 6, 8, 9, 16, and 18. Yeah, none of those are common factors. All right, well, looks like we only have 2 common factors. That's okay. Yeah, we'd never know how many are going to be there. Those are our common factors for at least 16 and 18. But you see, you got to check the whole list here. You don't just stop there at 1 and 2. Make sure you take your time, because sometimes, at least for me, like there may be like, I may get this 18 mixed up with this 8, but in actuality, maybe later on there's another 18 somewhere. So just be careful with that. Okay, let's look at all the common factors of 25 and 54. So 25, well, I know it's divisible, of course, by 1 in itself. So that's a factor pair. The next one I know of is 5 and 5, and that's all I know. So factors of 25 as a list would be 1, 5, and 25. That's it. Now let's go to 54. Of course, 1 times 54 works. 54 is a unique number because it is divisible by 2. Now, we don't have our 2 multiplication tables memorized to 54. So a little bit of long division here. 54 divided by 2. 2 goes into 5 2 times. 2 times 2 is 4. I'll drop the 4 to make it 14. 2 goes into 14 7 times. 7 times 2 is 14. So a remainder of 0 just as planned. So that means it would be 2 times 27. Now, whether we notice this or not, I would take the 5 and the 4 and add them together to get 9, which means that 9 is a multiple of 3, meaning 54 is also divisible by 3. So we're going to have to use some long division for this one too. That's all right. Divide by 3. 3 goes into 5 once. 1 times 3 is 3. We used a 3, got 2 left. Make it 24. 3 goes into 24 8 times. 8 times 3 is 24, so nothing remaining here. But that would be 3 times 18. Now you see as we go down this list, these numbers are getting closer together, like 1 and 25. Then they were exactly the same, which won't always happen. But once I get as close as I possibly can together, then it's pretty much done. So 54, it's divisible by 2, but its other factor was 27, so it's not divisible by 4. The ones place value does not have a 5 or 0 in it, so it's not divisible by 5. But what I do notice is that it's divisible by 2 and 3, so it must be divisible by 6. The other way to notice is that 54 is a multiple of 6. So I'm not going to show the long division here. That'd be 6 times 9. Now again, these are two numbers that are fairly close together. Is it divisible by 7? No, it is not. Is it divisible by 8? No, because it wasn't divisible by 4. So these are my factors of 54. Let's go and list these out. 54 has factors of 1, 2, 3, 6, 9, 18, 27, and finally 54. So, is there any common factors? There is. It just happens to be the identity, which is 1. And that's all. That's all I can see. There was only 3 factors for 25. There's no 5 listed in here or 25. So 1 is the only common factor between these numbers. Okay, when we find our greatest common factor, you can list them in factor pairs, but prime factorization may help us here. And you don't have to use prime factorization. You can list the pairs like we did on the last 2 examples, but prime factorization is a very nice way to just keep dividing and not have to think, well, is it divisible by 4? Is it divisible by 6? Some of the ones that are kind of spanning off of the 2, 3, and 5, okay? So we can look at those ones and just kind of go from there, which is what prime factorization allows us to do. Again, is there a specific method that you're going to have to do? I don't think so, but on the assignment, it's possible that they may do so. So just be careful. So here we want the greatest common factor of 18 and 30. Now, I'm going to do this one the same way that we did the previous 2 examples. And then we will find the greatest common factor. And then I'm going to use prime factorization. You can see how that works. And then decide for yourself which one you like the best. So 18 factors would be 1 and 18, of course. I can split that up with 2 and 9, and then 3 and 6. Okay. So down here, I would just simply list factors of 18, which are 1, 2, 3, 6, 9, and 18. Okay, now I've got to go to 30 and start divvying it up. So that'd be 1 and 30. I'm going to skip the division, but that'd be 2 and 15, which may take some work to find. 3 and 10 is part of our multiplication table. It's not divisible by 4, but it is divisible by 5 and 6. So 30 then would be divisible. Let's put that on there. 30 is divisible by 1, 2, 3, 5, 6, 10, and, well, 15 and 30. There we go. Okay, so again, same thing here. What are the common factors? Well, our common factors would be numbers like 1, 2, 3, and 6. So we can list these 1, 2, 3, and 6. And 6 right there is the biggest or greatest. So we would say the greatest common factor of 8 and 13 is 6. Okay, now, how does this work with prime factorization? Well, prime factorization, let's do both. 18 would factor into, again, it would use a factor tree. That'd be 2 and 9, or 3 and 6, doesn't matter. 2 is prime, and then 9 splits up into 3 and 3. Okay, so for my 18, using prime factorization method, so if you need to draw a line through there, that's fine. But 18 is the same as 2 times 3 times 3. There's multiplication. And then we do 30. Okay, so 30. I would probably use 3 and 10 just because of the 0 and the 1's place value. 3 is prime. 10 would be 2 and 5. Okay, so 30 breaks up into the prime factors of, I'm going to switch the order just for convenience, 2 times 3 times 5. Okay, now, should you use exponents when using prime factorization when finding the greatest common factor? You should not. But now what I do is I still find our common factors. Okay, well, my common factors, here's a set of 2's that are common factors. Here's a set of 3's that are common factors. Okay, now once it's used up, it's no longer there, so I can't say this 3 pairs up with the purple 3 because I already used the purple 3 with the red 3 already. So these are factors, and since they are factors, we multiply them together, and that would give us the greatest common factor, which, as far as I can tell, 2 times 3 is 6. It's the same exact answer that we got over here. Okay, so it doesn't matter which method you use, you get the same answer as you should, but you to choose which one you want to use. On the next problem, I'm going to use prime factorization, but again, if you want to make the lists, that's fine as well. So on this one, I've got 8 and 12. Again, prime factorization. Let's start with 8. As a factor tree, I would say 2 and 4. You could say 4 and 2. It doesn't matter. And then 4 splits up into 2 and 2. Once again, I'm circling all my prime factors, so just below it, I know 8 is the same as 2 times 2 times 2. And we do not want the exponent on this one because we need to see those factors. 12 also divisible by 2, that'd be 2 and 6. If you said 3 and 4, you got it. But 6 splits up into 3 and 2 as well. Okay, so my 12 splits up into 2 times 3 times 2. All prime factors. Now I need my common prime factors, which are, well, there's a set of 2's. Highlight those, there's my 2's. That's a set of 2's right there. Next set, 2 and 3, no good, but, and again, this 2 right here, my purple 2, I'm pairing with the one just above it just because it's convenient. Some students would say it pairs with that too. It doesn't really matter. All that matters is that I have another set of 2's that are common factors. So if I multiply those together, I have my greatest common factor, or GCF, doesn't matter, but 2 times 2 is 4, meaning 8 is divisible by 4 and 12 is divisible by 4. 4 is the biggest number we can divide those by, and 4 then is our greatest common factor. Now, if you made a list, again, these numbers are fairly small, so making a list, maybe that wouldn't take as long. The main thing you need to do is get the same answer we got is 4. So knowing your multiples is going to help as well. The product of a number and a natural or counting number. So you're going to start by making a list of the multiples by multiplying by 1, 2, 3. It's kind of like what we did when we were doing division in Module 1. And you just kind of make a list of multiples as you go up. Now, you may have to go past 9, so addition may not be so pleasant, but you can use addition if you need to, which is what we can do, all right? It's kind of like what we're doing when we make a list for division, right? Now, in our multiplication table, it's all of the products of numbers with other numbers. For example, in the table, you would notice that 3 times 4 is 12, right? So in other words, the fourth multiple of 3 is 12, or the third multiple of 4 is 12. Same if you did something like 5 times 6, which is 30. So 30 is the sixth multiple of 5, or 30 is the fifth multiple of 6. Doesn't matter, because we're describing factors and products here. Factors, there's 2 factors in every multiplication problem, or more. There could be more. So this is the first 5 multiples of 17. Well, 17 is its own first multiple. Okay, so there's our first multiple. Now, if I want the second multiple, which I do, then I would simply add 17 to 17. So 7 plus 7 is 14, carry the 1. 1 plus 1 plus 1 is 3, and this is my second multiple. Continuing, I would simply just add another 17 there, and that would give me 4 plus 7 is 11, carry the 1. 1 plus 3 plus 1 is 5, and there's my third multiple. Okay, we only wanted the first 5 multiples, so we're going to add another 17. This will be our fourth multiple. 1 plus 7 is 8, 5 plus 1 is 6. So 68 is the fourth multiple of 17. And then finally, we would simply add another 17 to get the fifth multiple of 17. So 8 plus 7 is 15, carry the 1. 1 plus 6 is 7, plus another 1 is 8. 85. That would be our fifth multiple of 17. So to make this list a little bit more pleasant to look at, 17 is the first multiple, 34 is the second multiple, 51 is the third multiple, 68 the fourth multiple, and 85 is the fifth multiple of 17. And we did it with addition, just like we would. Again, we've seen this before, when we were making tables on the side in order to do some long division. Now, if we want common multiples, it's possible that you may have to go beyond this, and that's okay if you do. Okay, so listing the first 9 multiples of 8, well, you can start with 8, and then adding another 8 would be 16. Really, this is just making the list of the values from the multiplication table. 8 times 3 is 24. 8 times 4 is 32. 8 times 5 is 40. 8 times 6 is 48. 8 times 7 is 56. 8 times 8 is 64. And 8 times 9 is 72. All right, so that's our first 9 multiples of 8. Again, you could have added. You could have said 8 plus 8 is 16, plus 8 is 24, plus 8 is 32, plus 8 is 40, plus 8 is 48, plus 8 is 56, plus 8 is 64, plus 8 is 72. But we just kind of did some multiplication, because the multiplication can make that fairly easy when we're dealing with numbers 0 through 12. So if I want common multiples, I can just make lists of each number and then find the lowest one that is in common. Okay, it's kind of like what we just did on that last problem, but now you're going to do it with 2 numbers until you find a common multiple between the 2. Now keep in mind when you're doing this for either method, we're going to show 2 methods. This is just our first. For either method, once you see these values are multiples of each other, well, what you may find rather is that one of the numbers is actually a multiple of the other one, in which case it is one of the 2 numbers that they give us may actually just be the lowest common multiple. So if I wanted multiples of 48, I'm gonna start with a few, all right? So 48, we'll do these ones in red. Okay, so again, that would be its own first multiple. I would add 48 to this, and that's gonna be 96. I'm skipping some math just for the sake of time and space here, but if I add another 48 to that, 6 plus 8 is 14, carry the 144. And we'll just do a few here, maybe 5. There's 3. Adding another 48 would make that a 12, 9, 192. And then fifth multiple. Let's see where this gets us, and then we'll see if it has any relationship to the 72. So that'd be 0, 1, 4, 240. Okay, so let's stop there. And again, that's my 48. The red numbers are my multiples of 48. Now I've got to test values of 72 as well. Okay, so I'm going to do 72 in green, and then I'm going to add the numbers in orange so we don't get them mixed up. 72 plus 72, 2 plus 2 is 4, 7 plus 7 is 14. Okay, so you could proceed, all right? You could say, well, you know what, I'm going to add another 72 to that 144. And yeah, I made it the wrong color, dang it. Because we wanted to show the multiples of 72, so I want those in green. Now, if by chance you just get kind of robotic about this, you could have said, well, I'll just keep adding 72, and then you get 216, and then you add another 72, and that would have given you 288 right there. Now, we don't need these, and, you know, depending on if you noticed or not, which we want you to notice. But you could have stopped right here, kind of like I did earlier, because 144 was shown here as the third multiple of 48. Now, if there was anything beneath that or lower than it, right, 48, 96, none of which are multiples of 72, you could circle those. But the lowest one that I see is 144. You could continue this pattern until you find something that matches. For example, what we don't want to do is say, well, you know what? I'm going to add 48 here to my 240, and then you get 288, right? Well, 288 is common with 288, but it's not the lowest, it's not the least common multiple. So you have to be careful. Always check your list to see if you saw the 288, you need to check your list further, I'm going to say up on the list to see if there's a lower one. Because if there is, you need to remember that that would be considered the least common multiple. Okay, so let's try 5 and 9. Again, we're just going to make lists here, but these ones are values we hope you have memorized. So we'd say 5. I'll do these ones in red. 10, 15, 20, 25, 30, 35, 40. I'm just going to list the first 12 because they're ones that we should have memorized. 5 times 9 is 45. 5 times 10 is 50. 5 times 11 is 55, and 5 times 12 is 60. Okay, so there's my first 12 multiples of 5. Let's get to the 9 then. So I'll do these ones in purple. 9 is its own first multiple. 18, 27, 36, 45, 54, and yeah, I know you could stop right here, but I'm going to continue. 63, 72, 81, and then finally 90. Now, my list is only showing one common multiple, and it is showing already. If you had continued your list down, looks like, I think 6 more times, for your 5s, you would have gotten down to 90, but the common multiple that I see, the least common multiple for these in my lists is 45. So the least common multiple of 5 and 9 is 45. That's it. Now, here's our second method for finding the lowest common multiple, and that is to use prime factors. Okay, so once you find common prime factors for the numbers, you just multiply the common factors, and that will give you the lowest common multiple. So if I was looking at the least common multiple of 32 and 8, and I think some of you know what the answer is already, and that's okay. It's possible that making a list would make this one easier, but what I'm going to do is I'm going to look at prime factorization of 32. There we go, it's a better 32. So that would be, well, I know it's 4 times 8, okay, and 4 splits up into 2 and 2. You could have divided 2 by 32, but it's not a multiplication fact we expect you to memorize. 8 splits up into 2 and 4. 2 is prime. But that 4 there is another 2 and 2. All right? So I'm going to list my prime factors of 32, which is 2 times 2 times 2 times 2 times 2. 5 2's all multiplied together. Now I'm going to use a factor tree for 8 as well, which we've already done over here. I use 2 and 4. 2 is prime, and then 4 is 2 and 2. Now again, some of you may have had the answer already because maybe these numbers you consider fairly easy. But I'm proceeding as though we didn't know any of that stuff because this may be fairly new. But 8 is 2 times 2 times 2. And what I need now is my common factors. Really common prime factors. So first up, I see a pair of 2's that match, a red and purple one. So it is a common prime factor. Same with this set of 2's right here, which is another common prime factor. Same with these 2 right here, which is another. Now, these are my common prime factors, 2 times 2 times 2. But what we need to do now is take the uncommon factors and multiply those as well. Well, what were the uncommon factors? Well, we had this 2, which didn't have a common factor, so I include it. And then this 2 as well, which I include here. And then this is what I got to multiply. I take all my common prime factor and then my uncommon prime factors, and we got to multiply these all together. Now, I'm going to skip some work here, but if you multiply these all together, you're going to get 32. Okay, now I pointed out 32. Some of you may have had 32 down earlier because you just know 32 is a multiple of 8, and that would work. But again, maybe that helps you understand this process because it's not always going to be this easy where it's like, oh, 32 is a multiple of 8, so I just know it's the least common multiple. Okay, that's fine. But the prime factorization may help with some different, bigger, or just really different numbers. So again, maybe listing would be better for 10 and 6. I'm going to use prime factorization just because it can be a nice way to do this. And in addition to that, prime factorization has shown in the past to help specifically 920 students. So when we get to actually the fraction stuff, I'm going to show it a couple different ways, which really just includes both these methods, kind of, okay? So to start, my first one is 10 there, right? So 10 just splits up between 5 and 2. That's its prime factors. So down beneath, I'm going to show 10 as the same as 5 times 2. 6, however, splits up into 3 and 2, both of which are prime. So again, my prime factors of 6 would be 3 times 2. So what I need is my common factors. Well, common prime factors. And that would be the set of 2's. They are common prime factors. So there's my common prime factors. But then I need to also multiply by my uncommon prime factors. So in the list, I have this 5 in red. It didn't have any common factors to pair with it. And I also have a purple 3 to include there. So when I multiply these together, I will have my least common multiple, which is 2 times 5 is 10, times 3 is 30. And that would be my lowest common multiple there. Now again, you could have come up with the same value with the list, or even if you just have your multiplication tables down, that would be fine. But again, this prime factorization stuff is going to help us. When we're looking at these as fractions, essentially these 2's become a phantom 1. We're going to talk more about that later on in this unit. But again, that gives us 2 solid methods to use in order to find the common multiples of values. But the nice thing is you get to choose which one you like the best. So here you are packing bags of food. Let's see what this is. At the local food pantry, you have 30 jars of tomato sauce and 24 cans of soup. You want each bag to have the same number of tomato sauce and soup. What is it? The cans? Yeah, cans, I guess. What is the greatest number of bags you can pack? How many jars of tomato sauce will each bag have, and how many cans of soup will each bag have as well? So the first question, what is the greatest number of bags you can pack? It's asking for the greatest common factor. That's what it's asking for there, because that means that both 30 and 24 would be divisible by the same number. So we're really answering the question, what is the greatest common factor here? Now, once we know what that number is, that's how many bags exist, or the greatest number of bags we can pack that have the same number of tomato and soup containers in them. So let's see if we can figure that out. And you can use the greatest common factor. To find the greatest common factor, you can use just straight division, finding factor pairs, or you can use prime factorization, and that would work too. So I'll do the work for 30 here on the left. Okay, so let's see if I can, there we go. So this would be tomato sauce that I'm working with here on the left. Ironically, I'm choosing red just because it's usually the first color I work with. But 30, now let's see. The prime factors of these aren't going to be too hard. So I'm going to say 1 and 30. All right, that's fine, and we need that 1 as well. Again, without showing the division, 2 and 15, 3 and 10, or 5 and 6. Okay, so those are my factors of 30, which, we're kind of listing there. But now, over here on the right, I'm going to do 24 in purple, just cans of soup, I guess. Okay, so again, 1 and 24 works, but 2 and 12 would work. Same with 3 and 8, as well as 4 and 6. So I'm using the listing method. Once again, the prime factorization would work here. Now, what's the biggest number in these lists? And that will be our greatest common factor, which tells us how many bags you can pack that have the same number of cans of soup and sauce in them. The one that I'm noticing here, I see the 1, 2, and 3, but I also see the biggest one is 6. So this means we can pack 6 bags that have the same amount of tomato sauce and soup in each bag. Well, if we're taking the tomato sauce and splitting it up into 6 bags, and we're starting with 30 cans, that tells us we're going to split them up or divide them into 6 bags, and that would tell us how many cans are in each bag, which is 5 cans. 5 tomato sauces. Oh, I guess they're jars. So we'll say 5 jars of tomato sauce, which I'm abbreviating because that's a lot of writing. Now, on the same idea here, how many cans of soup will be in each bag? So we're going to take the 24 cans of soup, and we're going to divide them into 6 bags. And this will tell us how many cans of soup are in each bag. 24 divided by 6 is 4. 4 cans of soup. Now again, this is for each bag, but it does help us to see how much of each is in each bag. So here's our 3 answers. 6 bags. In each bag will be 5 jars of tomato sauce and 4 cans of soup. Now think about this. Does it work? Okay, so 6 bags of 4 cans would be 24 cans of soup. That's how much we started with. So I'm just checking the conditions to make sure it works. If you have 5 jars of tomato sauce in 6 bags, that would be 30 jars. Okay, so again, it's showing we can divide 30 and 24 both by 6. It's the biggest number we can divide by. You could have said that you could have divided it into 3 bags. You could have divided it into two bags. But the most bags we can pack here, the greatest common factor is 6 bags. Okay, so that completes 2.1. If you have questions, I hope that I answered all the questions you may have on the assignment with the video. But if you have more questions, email is the best way to get a hold of me.